Hello, everyone. Hi, I hope you're having a good day, good morning, good afternoon. Welcome to our today Land Live introduction to regression models using R and tidymodels. So, my name is Eric Wanjau, our data scientist and researcher here at the Leeds Institute of Data Analytics at the University of Leeds. And today I'm joined by my lovely colleague Karani Wachira. So, Karani Wachira, how are you doing? Would you mind introducing yourself as we, get started in this exciting adventure ahead of us?
So, hello everyone. My name is Karani Wachira. I'm joining you from Kenya, Nyeri. I'm an undergraduate student at Kimathi University of Technology, and I'm also a lead of DeKUT R community, which is a data science community where we use R as our language of choice. Glad to be here and let's learn live.
Perfect, Karani. Nice. Nice to have you, Karani. So let's get to what we'll be doing today. So we're also joined by our moderator called Pascal Barome. So hi, Pascal. I know you're somewhere around in the probably in the chat or behind the scenes, but it's really nice to have you around. So Pascal is network and telecommunications engineer and also a Microsoft Last ambassador. So if you haven't heard of Microsoft Last ambassadors, are students who are trying to make technological impact in their community. So it's a really great community. Feel free to please join in the movement. So yeah, so today we will be speaking about introduction to regression using R and tidymodels. So this Learn Live session will probably follow a new R learning path in Microsoft Learn, focused on R and data science and fitting models, all using R and tidymodels. So today will be a follow-up of what we did last time. And last time we did exploited data analysis. This time we're moving a step further. We know how to do exploit analysis. So can we use what we know to, kind of start fitting some machine learning models and trying to predict things from our data? So feel free to code along with us and ask questions and throw in comments or suggestions or areas of improvement. So we hope it will be a good ride along and a good adventure for all of us. So these are our learning objectives for today. We'll learn when to use regression models and then how to train and evaluate regression models in good and acceptable statistical manner. And this will be guided by the tidy models framework in R. So if you're not familiar with the tidy models framework, this is a framework that allows you to do statistical learning and machine learning in the R language, very similar to what we have in scikit-learn if you're familiar with Python. So let's get started. So Karani, we'll be talking about regression and would you mind taking us through this first step of understanding what regression is and when to use regression before getting our hands started with the code? Over to you, Karani.
Okay, thank you very much, Eric. So, by regression, we define regression, whereby regression is a technique to use that uses models to predict a number. Bear in mind that regression aims at creating a model that can predict a numeric quantifiable value, and the value can be price, amount, size, or any scalar number. So this is what we'll be dealing with today, and we'll take an approach of whereby we'll use a real world example to tackle regression. In this real world example, we'll use an example of a bike rental company which wants to predict the expected number of rentals on a day in the future. A regression model can be used to predict this number. The company can create a model by using existing data which it collects, like the number of bike rented on a day, where the season and the day of the weeks were recorded. So kindly join us, as this will be a very interesting example to code along with us. Thank you, Eric.
All right, Karani. So we are, as you said, the plan is to predict, bike rentals, right? So Karani will do, what's the process that will we just fast dive into regression, or do you have a layout plan for us in terms of what will come after what, before getting into the actual doing regression? So do you have a solid plan for us here?
Yeah, I do have a solid plan, and recall that we are using the company that rents bikes. So to train a model, first we'll start with a data sample, and the data sample contains the features and known values for the label. In this case, we need the historical data which the company has been collecting. Then the next step will take is we'll take that data which the company has been collecting and split this data into two data sets. A data set for training, which is a training data set, whereby we'll train our model using that training data set. Then after training our model, we'll test our model. Those are the steps that we'll take to evaluate the model using the generated predictions. So on to our exercise of today,
Perfect,
whereby
Karani. So, Karani, as you were saying, you want us now to start doing the actual coding, right? Because I
yeah.
heard you're already preempting where we'll go. So, just we want to stop you a bit and tell our learners where we'll be doing the actual coding. So, probably I hinted this earlier. So, this is we'll be doing the actual coding. The link is in aka.ms/learnlive 2022 9098. I think it's being posted along somewhere in the chat. So this is how we'll be following along Karani as he's doing the the coding and the EDA,
Yeah.
the data splitting and fitting our models. So please feel free to join us along. And Karani, the floor is yours. Please take us through this exercise and the plan that you have for us.
So make sure that you use the link that our moderator has shared in the chat. And for this session, deal with we are training and evaluating a regression model, and it's the third exercise, I think, in the learn path. After accessing the learn path, make sure you activate your sandbox. After activating your sandbox, this, the sandbox contains a Jupyter notebook that has code chunks and some text to explain what we are doing by training and evaluating a regression model. So let us begin. The first code chunk, you use this play button to run this cell in order to load the packages that you are going to use for this exercise. So as I had said before, we are going to build a regression model, and this will involve the training process will fit the features to the known labels to define a general function that can be applied to new features for which the labels are known and predict them. Therefore, we can proceed on with the first step, which is loading our data set from this link, and we'll leverage the use of the tidyverse package, which is a package in R. Therefore, load your tidyverse using this link. After loading tidyverse, import your data, which is in a CSV format. After you import your data, take a glimpse of how does your data look, the data you'll be working with. You can do that by viewing your data. The name of your data is where the assigned it here is byte data. And from after running the code chunk, you can see your data, it's in a table. And you can also use another function in tidyverse, which is glimpse, and have a look of its structure. And the structure can shows the data types of your variables. You can see the DT data is a character, the season, which is a double. You can also see the rentals, which is a double, highlighted here. And you can observe that glimpse gives you the total number of rows which contain the observation and columns which contain the variables. Proceeding on, you can see the description of those rows and the total number of observation, whereby you can see it is the date on which the data was observed, the season, the year, the month, the holiday, the temperature, the apparent temperature, and the rentals. Make sure if you're coding along, you can see all this on your side and ask where you're stuck. You'll be helped. Okay, moving on to the next code chunk. What we want to achieve here is we can perform some EDA on our data. For example, we can add a new column named day to the data frame to add the column and extract the day component from the existing DT data column. So this is achieved first by loading the package date. After loading the package date from the data byte data, you can want to extract the month, the day from the DTE day. Remember the DTE day contains the days in which the bytes were entered. To extract the day, you can use the mutate function, which comes from the tidyverse, and be able to view and see that we have mutated the DTE variable, which was a character, into numerals. You can see the date where I wanted to achieve the year, the month, and the day. That's awesome. Still on some EDA, to start your analysis on the data, you can examine a few descriptive statistics which can quickly summarize the numeric features in the rental label column. You can achieve this by loading the summary tools. Summary tools, you will do that summary tool on your data, the byte data which you're working with, then be able to select the features that you want to see the summary. After doing that, you will get a summary of your data, whereby the statistics reveal some information which are very important about the distribution of the data. For this information, you can see that the mean daily renter is around 848, and there is a comparatively large standard deviation, and the deviation indicates a lot of variance in the number of rentals per day. Very interesting insights there. Make sure you see that on your side. They are very interesting insights, but there has to be a better way to clearly see these insights. And the best way to do this is to visualize your data. A very common type of visualization of numeric data are histograms and box plots. So let us use ggplot, which is part of the tidyverse, to visualize. Ggplot was also highlighted in our first episode, whereby they highlighted some of the uses of ggplots and how they work. So for this part, we are going to use ggplot and combine it with boxplot to achieve some visualization of our data. In this cell, you'll be able to view the appearance of your data in a plot. So as this cell runs, seems my sandbox is a little bit slow, but you'll be able to see some the output of what we have mapped. So for this code chunk, we said we'll use ggplot and map the aesthetic x, which is the rental, bike rentals, to create a histogram. We'll call the function geom histogram. Then the bins we specify behind it, then fill. This is the color. Then we'll be able to add the lines that indicate the mean and the median of our plots. Similarly, the box plots, we'll want to plot a box plot and we'll call the function geoboxplot, then fill the box plot, the color, and label our axis x label as rentals. Then combine them using this function. This function whereby the histogram will overlay the box plot. So as it loads, Eric, would you give us a hint why EDA is important before training a model?
Perfect, Karani. Yes. It's a it's a good question. It's I think you hit it to it earlier. So, at this point, you want just want to fit a regression model, but um, ideally, you want to know what kind of data is what kind of data we're dealing with. What's the distribution of the data? What columns are correlated with what could be more predictive. So this kinds of assist us to um, pass to the model. A model is good as the data it gives. So when was kind of to pass to the model, um, like the best variables in which it can extract a signal, and also in the long run allows us to know what kind of pre-processing techniques that we can use to so that the model can be able to better fit our data. So yeah, so I would say it's a really vital process of not only to the to the whole modeling process in general, but also as a data scientist, to understand what's really going on in the data. And um, yeah, and at least you have a good grip of the whole pipeline from from modeling to communicating the results probably later on. So it's a really vital process in the whole data science cycle. Yes, so that's how I'd frame it. Do you have anything to add yourself?
No, just say like things look better when they are visual than numbers, I would say.
Yeah, that's also an important point, Karani. So I would suggest, Karani, probably you try. I think this happens. You try
Yeah,
to uh to go up there and restart the kernel. Um, if you if you just you go to the top of the page, probably and interrupt the kernel or stop or restart it. It helps. So sorry for that. I don't know what happened.
all right. And I still have my minutes on my.
So probably, Karani, as you try and figure things out, I can also share my screen, if it's okay with you, so that we
Yeah,
can,
I will start.
as you give you time for your your machine for your tab to restart. How does that sound, Karani?
Yeah, that sounds nice.
Okay, so yes, so let's kick off where Karani stopped. Hopefully my screen is live. Yes, so as Karani was saying, was trying to try and combine multiple plots to see the distribution of what you want to predict. So we want to predict the rental, the number of rentals that will be, that the company will able to rent out in terms of bikes, and see whether there's any peculiar distribution of it. So as you can see, it's pretty, I would say almost a bell color, a normal distribution. But we have some outliers here, which were discussed last time, and these are numbers that really vary um, from the expected distribution. Like, they're really different from what we have from the rest of the data. So, but this is not really a big problem. Our rental distribution looks quite fine. So next thing we'd want to do is, now that we have a good indication of how our label is, what you want to predict, that's the rental distribution. And another good thing is to see how our variables look like. Yeah, so our predictors, I mean. So we'll start with the numeric features. So what we do here, we are um, just trying to analyze um, how the numeric features are distributed. So we have four numeric features. We have the temperature, the humidity, the wind speed, and the I think the A temp. The A temp was how the weather feels like. I think that's what was described up there. So, and again, we can see the numeric features seem to be kind of normally distributed, whereby this means that the mean and the median are close to the middle of the data. So this is a really this what this means in terms of modeling is that we won't have to transform these variables by doing transformers such as log transform, and this actually makes our modeling easier, as a model can really extract a good signal from these variables. So the next thing we can try and do is see how the categorical features look like, now that we have seen how the numeric features look like. And to do this, for the numeric features, we fitted, we plotted histograms. So for the categorical features, what we'll do is that we'll do some bar plots. So what basically here we're doing is that we're starting with the bike data, and then we are narrowing down to the categorical features using the command select. So select allows you to pick columns that you want. So some that I discussed last time. So, and then we kind of pivot longer the data so that we can be able to use ggplots facet trap commands. And what facet trap allows you to do is that instead of instead of graphing multiple instead of making multiple graphs using functions, allows you, kind of wraps that in for you, and such that you can create multiple graphics of the same geom. For instance, here we have created bar plots for all our categorical variables. So this is really interesting. You can see some features are distinguishable. Some look like they are almost not changing, and so these exceptions, from the uniformity of the rest, are such that you see there's like fewer holiday days than days there aren't. So you see, like, when a day is not a holiday, which is zero, is when you compare to days that are holiday, this is very like the data here, the column here is very sparse, and this helps to start from this ideas in your mind. How will I pre-process my data such that my model can be able to extract a signal from very low occurring columns, such as when days are holidays and when they're not. So, and I mean, this really is what we're talking about, the really important aspect of exploited data analysis before modeling. So with a little knowledge of how our categorical and numeric variables look like, the next step will be to start looking for the relationships between the features and the rentals. So, for instance, in numeric features, you want to see how the degree of correlation between a numeric column and the outcome column. So to do this, we first we take the numeric features, and then we create a new column called correlation coefficient, which calculates the correlation coefficients between the values in our the numeric values and the rentals which you want to predict, and then we pass them on to ggplot and make scatter plots. So what that will look like? It look like something like this, whereby as from a distance you can see like the ATEMP versus rentals. You can see like there's a slight, there's a slight uh I would say slant line that such that higher values of such as higher values of ATEMP correspond to higher values of rentals. So it's not really concrete, but it's apparent even given by the value here. And this is really opposite from, I would say, wind speed, where it seems high values of wind speed correspond to typical low values of rentals. So again, so these are some of the information. Just hold those thoughts. Just some information that will utilize in our modeling procedures, and we can calculate the correlation coefficients just directly, whereby we take the numeric features and then we use the function summarize to create a new data frame that calculates the correlation between the values and the numeric values and the rentals. And basically, this is what was the title of our plots. As you can see, each plot had a small title of the correlation coefficient and the what is being plotted. So as you can see, the the results are like really strong correlation, but we can see some vague diagonal trends, and either increasing or decreasing. So this is something that we can note uh, as we move forward. So, and then lastly, we can try and see how the categorical variables relate with what we want to predict, and that's the rentals. And to do this, we typically make box plots. So box plots allow you to kind of make summary statistics in terms of the minimum value, the maximum value, the median value by this line here, the lower quartile and the upper quartile. So as you can see here, we can see some variables such as they don't really have I would say distinctive a relationship between, they almost seem all of the same, seem almost alike. But you can see for things like holidays, when a day is a holiday, we tend to have higher number of rentals than when a day is not a holiday. So that's something we can note. So we also note something like in weekdays, day 6 and 0 tend to have higher number of rentals. So people will rent more on weekends or not. Um, uh, these are questions that we can continue doing exploit data analysis. So we can try and fit a model and try to get some of these answers. So see, the seasons vary in terms of how the bike rental company operates. So yeah, and that really comes to the end of our exploit data analysis. At least for now, we really have a good grip of what's happening within the data and some ideas that will explode down as we start building the models. So, Karani, I don't know if you're back with us, and you could, try and take us through creating a simple linear regression model, which is basically trying to fit a straight line through the data. Do you mind? Are you at part for you to take us through that?
Yeah. I'm back, but I'll take you through. But since my kernel doesn't load the code chunks,
Okay.
take me.
All right. That's really unfortunate. I'm so sorry about that. Um. Yes, but so do you mind then if I still do it, or perhaps I'll do it for now, and then if the code chunk starts running, I'll get back to you, right? Okay. So with the exploit data analysis we had, now it's time to train a regression model using tidymodels. So so the first thing is, as I said, please keep those insights that we have, that we saw in mind. So because we'll try and double down with them, in just a few moments. So what we're going to do is that now we're going to narrow down on some of the features that we saw are predictive or have some predictive value, and we'll ignore some, such as some such as the day. I don't think day would be a really good variable to include. So, and that's the advantage of exploit analysis. At least you know what you're going to fit in the data, no, in the model, I mean. So these are the features that we're going to be selecting. So we start with the bike data. So, and then we select these features. So these are the predictors that we've settled down for. And then we are going to encode some as categorical. So in R, categorical variables are known as factors. So categorical variables represent a category, such as whether a day is a season or not, whether a day is a working day or not, that's a category. Whether it's winter or fall, that's a category. Wind speed, that's numeric. These are a way of distinguishing the different columns in our data. So for columns 1 to 6, what you're saying is that mutate. So mutate allows you to modify columns. So mutate across column 1 to 6 and make them factors. So really succinct code that was covered last week. So, and then we'll just glimpse on our data. As Karani said, this just gives us the total number of rows, total number of columns, the type of our variables, and and what will be predicted, which is the rentals. So perfect. Time to start modeling. Karani put this really, really well, that we'll be starting with, after exploit data analysis, we'll be doing some data budgeting. And data budgeting really means is what portion of our data are we allocating to uh, different process of fitting and creating models. So at first, we want to split our data into a training and a testing set. So we want to create first a really basic model, really basic linear regression model. We are that will train on the training set and then evaluate on a testing set. So to do this, we first load in library tidymodels. So it's a set of packages that contains other packages that help you make good statistically correct models and guide you in the right path of doing that. So we take the bike select. So bike select, these are the variables that we chose to move forward with, and then we do a splitting specification. So splitting specification, what it does is that you give it the proportion that you want to go to training and the proportion that you want to go to testing. So for instance, you want 70% of our data to go to training and the rest to testing. So we say proportion is 0.7. And then because we realized that the holiday data, the holiday column, if you remember, the days that were holidays were really sparse. So we don't want, because the splitting is usually random. So we we want at least to include some of those days that were holidays, or else they may not appear at all, either in the training or the testing set. So that's what Strata does. So, and once one makes a splitting specification, the next step is to extract the data in each split. So, and to do this, we use two functions. One function is known as training, and the next function is known as testing. So, Karani, if you're here, what does training and testing do? Because I've not mentioned that. You just say it's function that extract things. So, what do you think training does for the splitting specification?
So the training splits the data, a bigger chunk of the data, which we'll use for training our model, is the one that we use the training dataset. So training function, we are going to pass the byte split dataset, whereby we'll use the 70% of the data in training. Then when we pass in the test function, we'll pass in our dataset, the 30% that remained from the 70, which will use it to evaluate how good did our model train in the first dataset, subset of the dataset. Yeah.
Perfect, Karani. Thank you for that. Yeah, so very well said. So training extracts the training data, testing extracts the testing data from our bike split. So yes, so Karani,
Yeah.
because you're here, uh,
Yeah.
you have to take us through the building fast. Before embarking on more complex machine learning models, which we'll be doing, we are starting with a linear regression algorithm,
Yeah.
right? So, which is
Yeah.
basically trying to make a straight line through the rentals and trying to reduce the residuals. So, Karani, now that we have our training and testing set, what do we need to build um, a model specification in tidymodels?
So in tidymodels being a framework means it contains packages in it which we'll use in doing our model specification. So there are very important three model specification concepts that we should know. One is we should define the model type. The model type, it means is is the model type a regression or decision tree models? And for this module, we are taking the learners through a logistic regression. That is the first concept that you should specify in your model. The second one is the model engine. The model engine means it's a computational tool that you use to fit the models. And there are model engine in R packages such as linear models, which we are using today, or Ranger. The third concept or specification we should do is we should need to define the mode. The mode, it includes options like, are we doing a regression? Do you want a regression or a classification? That is what we mean by defining the interface of the models. And that we are building that in the next code chunk, where we can see that we are passing in the linear regression as our type, our engine LM linear model, as we said, use in the set engine function, and then we set the mode as regression. What we hope to achieve today. Back to you, Eric.
Perfect. Yes. So getting a little bit jitters there. Yeah, so it's run, and yeah, thank you, Karani, for really explaining that well. The steps to building a model specification. So it's as you say, it's like define the type of model, want a linear regression, and the engine, the package is LM, and the mode, which is regression. What you want to do, and once we run these, we should just see, hopefully that runs. Okay, so that is running. So Karani, now we have, so we are at a point, Karani, where we have the data, right? We have the training data. We have defined a model specification, whereby it's a linear regression model that will be powered by the LM engine, the LM package in R, and the LM package is for doing regression. So Karani, I think the next step now is we can fit the model, right? We can start training. So would you mind taking us, how then do we tell our model, this is the data, this is what you want to predict, and this is our labels, and these are our predictors. So would you mind taking us through that, Karani?
Yeah, sure, sure. So to achieve that, in this exercise, remember on the subtopic, the first word was train a linear regression model. So in this next part, we'll do exactly that, whereby we want, we'll assign it to this variable and name it LM module. Then pipe the linear model specification which we defined above linear model specification, pipe it into the fit function. So into the fit function, what are we predicting? We want to predict the rentals. After we predict the rentals, we use the tilde key which you can find on your laptop, control and the button below the escape on the normal keyboard. Therefore, the rentals, you'll input the rentals tilde all, then use the training dataset which we split. After doing that, you run the code chunk, then print the model object which you have fitted. After fitting, there are coefficients that the model learned during training which will be highlighted on your output.
Perfect, Karani. That's really well explained. Thank you so much for that. So yeah, so yeah, so I mean that was quite easy. So basically we fit a straight line through the data, fit a linear regression model. These are the coefficients for it. So for those who are familiar, we know with the linear regression model, what you're trying to do is trying to find how each column is linearly related to the output in terms of an equation such as y is equals to mx plus c. So these are the coefficients associated with each column, and these are what the learn. This is what the model training was doing behind the scenes, learning these coefficients. So Karani, uh, training a model is just one part of the process. We've trained a model. How uh, and remember, we split the data into training and testing, right? Um, so how do we know how a model has performed? Like, should we should we uh, evaluate it on the training data again, or how do you go about that, Karani? You're the expert here.
So, so the next step after training, we need to introduce new data whereby we can evaluate how well our model was trained. Remember, we split our data. 70% we used in training and 30% is the subset data that we'll use in predicting, predicting, otherwise known as evaluating. So in the code chunk, our linear model, which we defined above, and we have already trained it, will pass the predict function. Predict functions comes from the parsnib package, which is a package within the tidymodels framework. In the predict function, pass in your training dataset, which was bike underscore test. After you do that, run the code predict. Then, because we want we can take a glimpse of only the first five observations of our predictions so as to make our chunk cleaner and even for a better visualization of how our model predicted. So when you run that code chunk, you'll be able to get the subsequent operation of how your model performed. Very true.
Perfect. Yes. At this point, Karani, um, we know there's one point you said it's better to visualize things. We've come along. We've split the data. We've trained our model, our linear regression model. We have evaluated it on the test set to see how well it performs. We've made predictions with it, and yes, uh, time to visualize it, like to see how good or bad. Because comparing this side by side isn't really helpful. There are better ways to evaluate this. So as a first, we can try visualizing the results. So, Karani, what do you think this shows us? Because you've taken the results, you've passed it on to ggplot, and you said on the x-axis, give me the actual labels, which are the rentals, and the y-axis, the predictions. And then, because our linear regression model tries to make a straight line through the data, we've also uh, overlaid one, and yeah, and so what does this tell us, Karani? Do you think we are heading somewhere, or what do you think?
So after we can say there is definitely a diagonal trend which can be observed well on that plot. And the intersection of the predicted and actual values are generally following a path of the trend line. But you can also note there's a fair amount of difference between an ideal function represented by the line, and also you can say there's a difference between the label predicted when model applies the coefficients learned during training, and you, you can observe that in that visualization.
Perfect, Karani. Yes. So with this, better ways than also to eyeball through the data and seeing the diagonal trend and how off our actual labels are from the predicted labels, we can narrow down on some well-proven statistics that help us do this. One is we're going to be dealing with two, I guess, um, in this module. One uh, is the mean squared error. Is the mean squared error. So the mean squared error is the square difference between the actual and predicted value. And then, so for instance, you take the predicted value and the rentals, you subtract them, and then you square them. But what is usually more intuitive is the root mean squared error, because the root mean squared error uh, is usually in the same usually in the same unit as your outcome. So the root mean squared error is always preferred than the mean squared error. So and the lower the root mean squared error, that means the lower the error between your the actual labels and what you want to predict. And in a very simplistic sense, root mean squared error tells you the average number of rentals by which the predictions are wrong. And there's also another metric known as the R squared. The R squared basically what it tells you is the amount of variance, or how much information can your model, um, how much information can the model account for. How much can it explain of what is happening within the data. As you say, a model just tries to capture the signal that is within the underlying predictors and variables. So that's usually quantified by the R squared. So a higher R squared typically means your model is really able to explain to a higher extent of what's really happening within the data. So to evaluate this, Karani,
Yeah.
there's a package called the yardstick, right? So I see here we have a function called metric set. So would you mind explaining what that does? Because like I said, we have a metric set and then we're passing it root mean squared and r squared. Um, yes. So would you mind explaining that, Karani, as we wrap up this first section?
So as we wrap up, we'll try to evaluate the metrics of how good was the model train, how good did it predict. So we'll pass the metric set. In the metric set, we'll pass the root mean squared error and RSQ and evaluate these two in the following code, and you'll be able to see to evaluate against the data, your data, and the results, and the rentals, and the truth, and be able to evaluate really did it did it predict to according to what you expected. And this is the best method. You have quantified the ability of your model to predict the number of rentals, and it has some, and you can observe that it has some predictive powers, but I still think we can do better.
Yeah, me too, Karai. I still think this we can do better. There's so many things. But this was a good baseline, right? Having this is a good baseline. At least we know what we can beat, right? What we are supposed to beat. So yeah. So this typical the first the fast process, starting off with a really simplistic models and then trying to build up on that. So from the metrics, you can see that you have the model can explain about 67% of what's happening in the day, 67% of the variance, and our predictions are off by around 395 bike rentals. So yeah, so this is where we are at. So yeah, so let's see how to go or how we could try and improve this and other statistically correct methods that you can apply to get better predictions. So I'll take us back to our slides now. So um, so that we can head off to seeing how we can how we can improve what the score we just showcased. So and yes, so let's do that. So if we go back to our slides, what the next step is oh, it's actually a knowledge check, Karani. So next
Yeah.
step is a knowledge check that asks this question. The Tidymodel model frameworks was used in R to train a regression model from a data set of sales data. So to evaluate the model to ensure it will predict accurately with new data, what should be done? So this is basically based on what we did, what we've just been doing. So and just asked us what a good methodology to follow on fitting models. Should we first split the data into two randomly subsets? Use one to train the model and the other subset and the other subset to evaluate it. That's the first option. Or second, should we use all the data to train the model, then use all the data to evaluate it? Okay, that sounds possible too. And that is train the model by using only the feature columns, then evaluate it using only the label column. So yes, so this is a fast kind of knowledge
So
check to see how things are going and seeing if we're all following or we're all on the same page and where else we can have questions. So please, if you have any questions, please feel free to drop them in now. But yeah, so what yeah, just giving a sec or two to try and answer this. Yes. So, Karani, are you thinking of an answer to this yet, or do you have an answer, or is it a difficult question?
I believe I have an answer, but I would, I would wish our audience can engage with us via the link that has been posted by our moderator, and let us see if you are keen as we went through the exercise, and look forward to seeing your answers. But I have a clear idea of the answer.
Perfect. Yes. So okay. So I think we have we've given some good enough time for people to
Yeah,
put in their answers in the chat. So Karani, because this is supposed to be, you taking us through this.
yeah.
Do you mind telling us what the answer, what you think the answer is, and why?
The answer is our answer is A, because
Okay.
even in our objectives, the first thing you should do is split your data randomly. The word randomly is very key because you don't want your data like you have split only the first five rows or columns. A random split data set is good, and you use one subset to train and the other to evaluate your model. So A is our correct answer.
All right. Yes. Let's see whether, yeah. So yeah, A is our correct answer. So we depending on how the data is, we typically split it, that the training so the training set is for training the model, the evaluate the test set is to see how well the model perform out there in the wild, or or on new data. So we can discuss B. So B was wrong, because we if we use all the data to train the model and then use all the data to evaluate, then we are doing something known as resubstitution. It's a common error in machine learning, whereby you are evaluating on the data that you trained on. So this is really dangerous, especially in some um, good powerful machine learning techniques, such as tree models, or such or ensemble models, such as boosted trees or random forest, because they have a high ability to memorize the data, and they can give very optimistic results. So you don't want to train and test on the same data, because you'll be kind of lying to yourself. So yeah, so that's why B was wrong. C was wrong because C was wrong, because because training the models using only the feature columns. Training a model, especially in supervised learning, is you want to train a model to predict something. So there's a label that's targeting that you want um, to predict. So you can't train on only the feature column. So that's why C was wrong. So, but anyhow, thank you for everyone who voted. A is the correct answer. Thank you, Karani. So, can we do better? There's a question. Karani said we can do better, indeed. So let's see how we can try and improve what we did, and probably provide you with a guidance how you can probably do it on yourself, and try and beat the linear regression model that we just built. So the first thing is to do feature engineering. So tidymodels provides you with a package called recipes for doing feature engineering. So feature engineering basically is where you are kind of restructuring your variables, such that a model can fit the data well. So some of these processes that you use to modify your columns to make a model be able to fit it well is something like normalizing the data. So especially in linear models, normalizing would help to prevent columns or predictors that have high values from scoring higher than the ones that have low values. So this usually that's one feature engineering step, normalizing your numeric column. Probably another feature engineering step is simply replacing missing values. Because sometimes missing values can either skew the results, or make a model not run completely, because some have no ways of handling missing values. So one way of imputing missing values is by probably something like step impute mean, whereby you replace the missing values with the mean value for that particular column. So this is one way you can use, depending on the model, you can use to kind of modify your columns so that the model can extract the signal better. So that's one thing, feature engineering, and it's done by packaging tidymodels as recipes. So another way we could try is try a different model altogether. So at least we're at a point where we have um, you know uh, people in the open source community who have done really great work in open sourcing some of these engines. I'm saying packages for that help us fit different models. So, for instance, we can try a model such as boosted trees. So boosted trees. That is provided by packages such as XGBoost allows you to build an ensemble of tree models such that each each subsequent model is built on top of the other in a way to reduce the error done by the previous tree. So these are some of the this some of the model you can try out, a different model, and then probably compare performance, or even do something like model stacking, to try just improve performance. So there are other different models, of course. You can try a random forest or a linear regression model that is penalized, such as a lasso. Most of these are discussed in our learning path. So yeah, so that's really another way of trying to see how you can you can improve from the base linear model. So another thing that one can do is something called model tuning, and this is typically associated with some models. For instance, uh, boosted trees models have tuning parameters. And what really is model tuning? What is it all about? You find out that some model parameters cannot be directly estimated from the training data. So you see, unlike a linear model where we estimate the coefficients associated with each column. So for some models such as let's say the boosted trees that we're going to be doing, you find out that some parameters such as the number of trees, because we are fitting trees sequentially on top of each other. So if you fit too many trees, then you have a high risk of overfitting. So a good tuning parameter will be the number of trees to tune. So what we do is, instead of learning this kind of hyperparameters during model training, we tune them. And tuning, in very simple terms, means this is trying out different values. Say, try out 5 trees, 10 trees, 30 trees, measure performance, see how the model performs. You see how the model performs in doing the prediction, and then pick the best. So that's usually what model tuning is just trying out different models, measuring their performance and picking the best. And yeah, so that's there's really no big magic in that. And tidymodels really provides a nice interface for you to do this. So yeah, so this I would say these are some of the ways that we'll try, especially in this Sun Life, to try and improve our previous model performance. So let's pause for a second. i- as, uh, and think of something, right? So now that we have a linear model and then we want to create a boosted trees model that will tune, there's a question comes up that is really apparent in real world situation, and it's really phrased well in the book Tidy Modeling with R, and the issue of the quagmire is this. So you have to split your data as you did into training and testing, right? And uh, the testing set is precious. We only want we only want to use the testing set once we are sure that this is the model that I want to put into production. This is the model that I want to, to share it with colleagues. So how then do we narrow down from, we have a linear model, we have this number of boosted trees model that we want to trial. So how do we decide what we're going to go forward with? And we know that we cannot repredict on the training set, because that will give us overly optimistic results. So since we cannot repredict on the training set, and since our testing set cannot be used to decide what model we are going to go forward with, what we usually do in machine learning and in good statistical practices is something known as resampling. So resampling really is the process of creating simulated data sets that allow you to evaluate model performance. So, and typically it goes something like this. So you have all your data, you split it into training and testing sets like we did, and then on the training set, we kind of create these new simulated data sets that are either random combinations of each other. Something that allows you not to touch the testing set, but to do all your training and kind of evaluation and decision making using the training data before picking up this one good model and going forward with it in the testing and probably deployment and all that stuff. So one model resampling technique is known as cross validation. So in cross validation, what you do is that you randomly take your training data and then you split it into I would say into k different folds or k different groups. So what you do is that for each iteration, you you kind of shield one group and use the rest for training, and then you use one for assessment, and then for the next for the next loop you go to you use another fold for evaluation, and the rest you do it for analysis for training the different models. So this goes on again, until you have covered all the k different splits that you made. So with this, first say you did 10 different splits, so 10 k is equals 10 cross validation. We'll end up training a model 10 different times and evaluating it 10 different times, and then averaging the results. So what this allows you to do, or how this gives you as a data scientist, is a way that you can be able to compare, this is how this linear model would perform in real world, and this is how this XGBoost model perform the real world without actually touching the testing set. And then the good thing about cross-validation and model resampling in general is that the performance you get, they're not usually very different from how you get on the testing set. So it's a good way of comparing models and picking the decision of what to go on with next. So yeah, and that kind of brings us to how we can improve the model performance, and we'll try and quickly go through some of this in in a coding session in just a minute. So now let's move over to so let's now move over to our coding environment in VS Code. So please feel free to code along. So this is based on the learning path, and it will be learning path the exercise 7, I think. Yeah, exercise 7, called optimize and save models. So that's the one that we'll be using. That's the one that we'll be following along. So let's get to that. So please tell me whether my screen is visible, and yes, so and we can try and follow along. So I'll be doing it in my local environment here on VS Code, but but really this is on this is on exercise 7, optimize and save models in LAN. Just trying to reduce in case the kernel breaks or something. So what I'll be doing is I'll just be adding to what Karani did, or what we did with Karani. So basically, I just load everything we did up to this point, no EDA. So basically, loading in the packages which you want. So tidyverse, tidymodels, sudo date, polytia, importing the data, uh, doing some initial model selection of the features and the labels we found that were good, splitting the data like we did into 70% for training and 30% for testing. And
Eric,
then,
Eric,
yes.
I believe you have not shared your screen yet.
Oh, okay. What about now?
Yeah,
Um,
now it's visible.
Yes, sorry about that. Yes, so sorry about that. So as I was saying, we'll be dealing with exercise 7. So exercise 7 in the LAN module that we're just dealing with some few moments ago. So what I was saying is that we'll basically follow the same initial procedure, that is importing the data, selecting the desired features or labels, splitting the data uh, into a training and testing set, and then extracting the training data and the testing data from each split, just like we saw using the training and testing commands. And yes, specifying the regression metric, that's the root mean squared error and the R squared. So once we run that, we have what we had from last time, like somehow a similar environment from what we had. So we have again 511 rows, 220 columns. So this is the model that Karani guided us in building the linear regression model specification. So the specification, the type is linear regression again. The engine is the LM engine, and the mode is regression, of course. So what we've now tried to do is try to see whether by whether by doing what, whether by pre-processing our data using recipes, we can try and get a better fit than what we previously had, right? So, some of this we spoke about, such as scaling and normalizing the data. Uh, so it is very useful in linear models because um, normalizing numeric features such that they're in the same scale prevents features with large values from producing coefficients that disappropriately affect the predictions. So, consider a variable that has a range 1,000 to 10,000, and now that has a range 0 to 0.9. So that would bring a problem in linear models. So that's one way of kind of feature engineering. So the second, probably worth noting, is encoding categorical variables, and typically this means is you know uh, categorical variables such as you see small, medium, large. You can you can you can kind of convert them to numeric variables, because these models learn on numbers. That's how they learn the relationship between the data. So we can do something known as ordinal encoding, which is basically replacing each categorical variable with a number. Or we can do something called you can create something known as dummy or indicator variables, such that each each categorical variable, you're either replacing it with a 0 or 1, depending on whether it occurs or not. So, Fox maybe, for instance, here small, medium, and large. We can have medium as 0, 1, 0, and large as 0, 0, 1. We can also have small as 1, 0, 0. So in R, the convention is usually to exclude the first level, in our case S, and this is usually due to simplicity and reducing linear dependency. And also this really varies with the model, because this is really good in linear models, but as you'll see on XGBoost models where linear dependencies are not an issue, you can do the whole S, M, and L. So yeah, so this is some of the pre-processing that I was talking about. So let's create a recipe for our data, right? So to create a recipe or a pre-processing steps, we use the recipe function. So the recipe function, what it does, it takes in a formula, and this formula is rentals, um, uh, and then the tilde, and then a dot. So as Karani explained this just means we're telling our recipe the rentals is the outcome. This is what you want to predict, and everything else is our predictors. And then return the recipe. You're going to infer that data from the bike train. So you're going to infer this information of rentals and everything else from the bike train data set, from the train data set. This typical what to use. So and then we are going to add a series of steps that will define the pre-processing. So the first thing is we're going to do something known as step dummy. So step dummy is usually used to create dummy variables, as you've seen up here. So this is what step dummy will do. So step dummy will create indicator variables for all the nominal predictors. And nominal predictors is just a way of saying these are categorical variables, the variables that we said, are factors. So we'll first create dummy variables for all nominal predictors, and then we'll also do another pre-processing step. Um, all this is based on exploited data analysis. That's why I said, just keep it in mind. Another pre-processing step we do is step near zero variance, step NZV. So step NZV, what it does, from the documentation right here, graciously given to us in VS Code, it creates a specification of a recipe that will potentially remove variables that are highly sparse and unbalanced. So, and if you remember, we have some variables whereby that were very sparse. For instance, the holiday variable, right? Remember, like there were our data had very little holiday days because they were very minimal than days that are not the holidays. So during the splitting, we can we can get probably very few holiday days or others. There are pretty other number of columns that were a bit sparse. So what step near zero variance tells the recipe is remove all uh, all predictors that yeah that are potential that they'll be that they'll have like zero variance, like they'll be very sparse, they won't have very good distinction. So that's what step NZV does, and this is usually really useful, especially in linear models, um, uh, where you want to remove sparse variables. So the next thing we're going to do is to center and scale the numeric predictors. So this is basically, as you said, trying to reduce the effect of large numbers on small numbers. So that's what we're going to do. So step normalize, and this will be applied to all the numeric predictors. And then another thing we can do is do something known as a step interact. So step interact in modeling. So we have variable, we have columns, or we have predictors that yes influence a prediction, but they are also contingent on other predictors. So for instance, we can predict rentals given the apparent temperature, right? But also the apparent temperature is sometimes dependent on the weekday, and sometimes the weekday is dependent on the season. So we can try and put in some of these, I would say, interaction to just try and make our linear model to kind of know some of these nonlinear relationships in the data. So that's one way of doing it. And lastly, we can reduce correlation among the predictors using a step known as step call. So this creates a recipe that will potentially remove variables that have absolutely large correlation. So in machine learning, you want to have I would say, simple models that in which the predictors are not very correlated with each other. So this helps this helps in avoiding large complex models, because having lots of predictors that are really correlated with each other, that doesn't do much predictive job. So these are some of the recipes that we can explore and see whether they play any role in helping the linear model in trying to predict our our rentals. So once we do that, the next thing is just printing out the recipe. This will tell you all the steps you did. So now once we have our model specification and our recipe, time to put them together into something known as a workflow. So, and typically what this allows you to do is allows you to bundle the recipe and the model specification such that you can have this one block of code that will first pre-process your data, normalize, remove near zero variance, create dummy variables, do all that pre-processing, and then fit the model in the model specification. So this is what a workflow does, and this is what the workflow will do and this is how we bundle the recipe and the model using a workflow. So a workflow, and then you add the recipe, and then you add a model. So yeah, so we're on the right path. So we've created we created a model definition, created a recipe, bundled them into a workflow, and then now it's time to see how uh, the model would perform using samples. So as we say, if the tester should not be immediately used, and the predicting on the training site is a bad idea, resampling methods such as cross-validation are usually the solution. So just little explanation again. Cross-validation, you random divide your data into V subsets, use one of the training folds for training, the rest for testing, then repeat this until you cover all the folds. So to do this, it's pretty straightforward. You just say to create, let's say, 5 folds. We'll say we use the function vfold cross validation. We put in the training set, the number of folds you want, and yes, and creating, and that create the and that really creates this randomly split and simulated data sets from our training set. So, and then finally the last thing um, is predicting on those resamples. So remember, these resamples are simulated data. So not actually the training data, they are a simulated version of it that will help us decide, are we going to pick this linear model that you have tried to do some pre-processing on, or because you're tuning XGBoost model, will we pick that? So these are just instructions on how to do that. We are just saying, we're just telling our resampling, save the predictions. So, but to actually fit the resamples, we actually fit the model and the resamples with a function that's fit resamples. So fit resamples takes in a linear a workflow, a trained workflow, no, a workflow that we specified, which is this. And then so it takes the workflow and defaults the simulated data sets, and then we say control is equals control bytes, and that will just say just save the prediction. We just want to visualize them, and then once we fit the resamples, once we fit the model on the resamples, we can collect the predictions, and also we can collect the metrics. So this already ran that because it takes a little while, but here are the metrics that we got. So by using the model, using the workflow that had all the pre-processing steps and and all that, on the resamples, it has a root mean squared error of 409.60. This means we are kind of off by around 409 rentals, and a R squared of 64%. So we are predicting 64% of what is happening in the data. We're able to account for that. So yes, so with this, this gives us a better indication of how the model would perform out there in the real world, and it's pretty useful because in the next steps we want to compare it with an XGBoost model. So let's try out an XGBoost model and then and see how we can we can compare it to what our linear model does, or the best of the linear model that you could find in the previous steps. So so as a first, we'll go through the steps again, and this is to create a tunable model specification. So again, we follow the process that Karani told us. We start with the model type, the engine, and the mode. So for the model type, we want a boosted trees model. And then we'll decide. Remember, boosted trees model builds many trees sequentially on top of each other with the aim of reducing the error for the previous tree. So because this data is small, we'll just use 50 trees. It will be good to tune it, to tune this value, but because of time and because it's a little computation intensive, I'll just say, oh, let's not tune trees. Let's tune something known as the tree depth, and this typically tells the tree during training you go up to this much, because boosted trees just fits um, normal tree models and then stacks them up together. The tree depth tells us how much far we're going to go, in splitting the data up to the very last leaf of the tree model. So this is something that we wouldn't know in advance. So that's why we tune it. So, and also the learning rate. So the learning rate basically is how much model parameters, how much rate are we going to change the model parameters. So remember, a high learning rate, the model will train faster, but can miss the global minima of or can miss the minimal error, and it trains very slowly. We cannot reach the expected or the desired error rate. So again, this is something we wouldn't know like in advance, so that's how we have to tune it. And tuning basically means we will try out very many different models and then pick the one that is best. So this is the tunable model specification. So for the recipes, we'll again create a recipe just like we did in the linear model. So it's still a recipe that says rentals, predicts everything. And then for our boosted trees, because it can learn these complex relationships between data without actual match, uh, actual match, you modifying the data or doing the process we did up here let's say of creating dummy variables or normalizing data. It can pretty much handle a lot of the pre-processing steps. So our recipe will be very easy. Will just to be normalizing the data, the numeric predictors, and doing dummy variables, because XGBoost does not have the capability to do that on its own. So this is usually very, really important. And then basically stack them up into a workflow and yes, get a boosted trees workflow, which tells you we're going to be tuning. Then we'll be tuning the tree depth and the learning rate. And then just wrapping up on this step, the next step is to create, this, as you said, tuning is basically trying out different values or different models and then seeing which performs best. So you have to create a grid of these values. So we create a grid of the tree depth and the learning rate, as you can see here. And then we say want 5 combinations of each. So 5 times 5, that's give us 25 models to try out. So these are the different combinations that we try out of tree depth and learning rate, and see which works best, and which can which can be the best candidate to choose from a linear model, from the XGBoost model. So this is done easily using the grid regular function. So once we have our set of values to choose from, the next thing now is to train this different combination of models and get the best. So again, we'll use the folds that we used before, so no need to run this. But then the most important thing now is to tune this. So to try and tune is just try with these parameters, where we use the tune grid function. The tune grid takes in a workflow, which is a recipe and a model specification, and the resamples. So the resamples are these folds that will train many models on, and the grid is the values, the different tree model combinations that you're going to try out. So I already ran this. This takes a couple of seconds to run. But once we run this, we tune the models. We can collect metrics that, like we did in the linear model, and visualize them. Actually, we can actually visualize them, and what you can see is that what we're seeing is a learning rate of around 0 point something here gives us a really good um, gives us really good R squared, and also the tree depth of I don't know around 4 gives us a good root mean squared error. So this is something we can visualize and see what combinations will likely result into the best either R squared or root mean squared error. But the best thing to get this is to use the function show best. So we take our grid and then we show the best. So show me the best root mean squared error. This is what I'm interested in. How of our models are in how of our models are doing prediction. So the best root mean squared error are these top 5 models. So a tree depth of 4 and a learning rate of 0.085 gives us the best root mean squared error.
Oh, Eric,
So yes,
unfortunately, we are run out of time.
yeah,
As you finalize,
yes,
can
yes.
you?
So this is perfect. Let me finalize on this. So yeah, so we can get the best root mean squared error, and you can see at this point, using our resamples, we are able to pick the boosted trees model because it had the best root mean squared error, uh, compared to our linear regression model, which had a root mean squared error of 409. So we have been successfully able to compare models without using the testing set, and this is usually really the beauty of the resamples. So allows you to compare different models, or to tune different models, and the last thing we can do is finalize the model. So take take this best combination. So the best tree, you're saying take the grid and give me the best model that had the best root mean squared error, and then finalize our models. That means taking the workflow and putting these values in it, and that's how you typically improve the um,
Yeah.
our regression results. So that's it. Then you can go ahead and follow the rest, such as now training it on the data, on the actual training data, and evaluating it. But yes, so that's what we have up to now. So I think this is what we'll wrap up with, right? Because I feel the next step is Fox joining us on the next challenge on classification. But at this point, we're able to use regression models to know how to use regression models and how to train and evaluate them, and get the best out of the data we have. So yeah, so please feel free to play along with the code after this, and yeah, so that's it from this part of improving the models that we built earlier. So Karani, do you have anything to say as we wrap this?
So I would encourage our runners to really go through the material on the module and be able. You can also share on the socials that you have completed a learn path and have fun and share with others too. And hope to see you on the next episode too.
Yeah, perfect, Karani. Thank you so much for joining us. And yes, and we encourage you to try it out yourself. And yes, please feel free to share, tag us, or ask questions. We're really here to help. So thank you, everyone, and see you soon. And happy learning.
Happy
Bye.
learning to you.
Thank you, Karani. Thank you, everyone.